introduction to where I come from. I come from a global network of campuses. NYU has 14 different campuses worldwide. There are 3 main campuses that are degree granting, and these are located in New York, in Abu Dhabi, and in Shanghai, and I'm located on NYU Abu Dhabi Shanghai campus. So on this campus, we have about 1,400 students. We have very diverse student group, more than 120 different nationalities, speaking more than 120 languages. Interestingly, we have 56% of our students female. Next, I'll show you what is my dream in haptics. And I've been long dreaming about this, what some people call the haptic aura, which is basically some magical haptic interface that surrounds entirely our body, that dissolves in our everyday life, completely transparent, portable, reaches out to every single dot on our skin, but this still remains a dream. Now, back to reality, I'd like to take you through some of the areas that I think are extremely important if we really want to make some progress into this direction, and that includes 3 different fields. One is providing ambient haptics, which involves both capturing haptic media and displaying haptic media in really novel, creative manners and ideas. Then we still need to look, we've been talking about what is the killer application in haptics. I think we need to explore even further out of this direction. And in particular, I'll take a couple of examples and show how we try to explore this further, particularly in effective haptics and in training and education. And last, that still remains a dream, is trying to model the human haptic system. I mean, we do a lot of experiments and we hire a lot of people, and this takes a lot of our resources and time. The dream here is to create a model that could behave like a human. And in that case, you can run all your psychophysical experiments with these models, and then life will be a lot easier for us, and we can automate lots of things. So here's a quick agenda for what I'm gonna do. Give you the mission statement of the lab, and then walk through these different topics. So we are interested in haptic science, in haptic interfaces, and in haptic applications. And only these 3, when they meet together at a very early stage in the design process, when creative, interesting things come up. In particular, we are working on contactless mid-air tactile stimulation using ultrasound. We're working also on contactless haptic modeling, where we're trying to use active thermography to characterize material surface properties and use that for haptic modeling. We're also looking into effective haptics. We're looking into haptic guidance, medical training. We've spent more than 2 years developing a research prototype that, as we speak today, is running an experiment with 45 different faculty at the College of Dentistry in New York. We're trying to build a periodontal simulation system for dental students. And finally, I'm going to give you a little bit of what we recently get involved in trying to understand the neuroscience behind mediated touch. So let's get started. Novel haptic interfaces. So I'm sure you're familiar with this. People have looked into using ultrasound to form a focal point of localized acoustic pressure in midair and try to make it strong enough so that our skin can pick it up, and then this will be a mid-air tactile stimulation. Works fine. We developed a system where you can load any arbitrary 3D object that converts to a point cloud. Every single point corresponds to a bunch of timing for all the transducers that need to be activating and leading the transducers, and that can be fed into the transducers array, but this is loaded all onto an FPGA so that we can do this a lot faster. So we implemented the hardware and we tried to build this in a customizable design. So we built a tile-based system so that we can extend it arbitrary. And then we tried it out, and that worked. So we could produce a single point of tactile stimulation. We could animate that single point. We could produce, if you move this animated point at a very high frequency, then you can get a conception of a floating 2D object in space, and then we tried eventually to try with 3D objects. So we characterized the system, and we found that we can successfully produce a single point of tactile stimulation, straight line, circle, and the upper hemisphere object, as you see. Then we went on to characterize this display, And we looked in particular into the most two important aspects. One is the maximum tactile force that these devices can produce, and the workspace. So we noticed that the maximum force doesn't really scale as you increase the number of transducers beyond a specific limit, and that makes sense because those transducers have limited directivity. In terms of workspace, apparently as you expand on the XY axis, then the workspace expands along the same directions, but along the Z axis, there's no much improvement, and now we understand the limitations of this technology. Next, of course, because this is a haptic device, we had to experiment and try it out with users. So we conducted an experiment where we tried to figure out whether people can recognize 2D objects. And then we used these 4 objects and we get good results, except that in many cases circle and straight line were confused, probably because of the limited resolution of the focal point that stimulates the palm of the user. Then we tried to combine this with the aerial imaging, and we tried to display texture in mid-air. And the way we did this is by just controlling the intensity of this fibrotactile pressure in mid-air. For example, in this case, we're having slices of different colors that correspond to different intensities of ultrasound. And then you could actually feel different texture. Of course, the resolution here is limited. One of the limitations of this technology is the audible noise. As you know, as you modulate the 40 kilohertz frequency of the ultrasound, then you get into the audible range. And that creates really unpleasant noise. So we try to handle this by taking that signal and even modulate it one further level with a usable audible signal. So now we created an audio haptic or audio tactile synchronized system. We also tried to optimize this further because of the so many limitations in this technology, and the first thing we thought was the transducer itself, and we think this is the bottleneck. So we tried to open this up, and if you look carefully, there's this matching layer here, conical shape matching layer, and that is designed to optimize transmission and reception at the same time, because this transducer was designed as an echo device transducer for proximity sensing. And that's not really what we're after. So we decided that we want to look into that and try to optimize it further. We looked into what would be the impedance, the acoustic impedance for that. We used some existing models to calculate, and we found this range. Then we tried to look into material that are out there, and the closest to this was aerogels. And if you know this aerogel material, they're extremely lightweight. They have a density close to the air, but they're very, very brittle. And this is why this didn't work out, because if you place this on top of a vibrating system, then it's going to break. So we thought of using aerogel alloys, and this is what we did. So we got this material, we machined it, we replaced the matching layer with this one, and we tried to compare the performance of this transducer to the original Murata transducer, and we found some good improvement. We found about 5-6 decibels of improvement in terms of the acoustic pressure and in terms also of the directivity, but this is not enough. We know that this is not enough because this is our target. We want to reach a point where we can stimulate 1 cube of meter of workspace, and that is not good enough for that. We want to stimulate up to or about 50 millinewtons everywhere in this workspace. We want to have flexible bending shapes so that they can take arbitrary shapes. We want to get completely rid of the audible noise. Power consumption is a big issue. There are discussions about are there any side effects for humans with ultrasound. All these discussions remain, but we stay committed to we are really interested in continuing this, and now we're fundamentally looking into a completely different technology to redesign the transducer. Let me move on quickly to effective haptics and why we're trying to study emotions and mediated touch in particular, because we know that there is a very special relationship between emotions and touch. In particular, both touch can express really nicely and kind of implicitly those emotions and can influence them. So effective haptics is an area where people are trying to look into how do we recognize, how do we display, how do we influence emotions using mediated touch. So to do that, we tried to build a system, and we were looking into what would be a reliable method of capturing human emotion, and we realized that EEG the brain signal would be one of the candidates. We did that, and then we tried to use vibrotactile stimulation to influence and to display the emotion. So I'll just quickly over the emotion recognition part. So the summary out of this is that we, with 32 different electrodes, with about 500 features, you can reach up to 92% accuracy for recognizing the valence and 96% for recognizing arousal. So now we have kind of an automatic way, a non-invasive way to recognize user emotion. Now, in terms of displaying emotions, we thought of using apparent tactile stimulation. And the way this is based on funneling illusion, where you have an array of ultrasound transducers, and then you can simulate apparent tactile motion. And in order to experiment with this, because there are so many parameters here, intensity, frequency, direction, location, there are many other parameters, so we decided to create a simple authoring tool to create what we call tactile gestures. And these are simply by moving, the user would move their finger in mid-air, and then we capture their movement, and we display a corresponding tactile stimulation. And then we hired a focus group where we looked into different combinations of those parameters to find relationships to different emotional responses. In particular, we looked at high-low, low-high valence arousal combination, and this focus group came up with these properties for those candidate patterns. Then we wanted to take this further and experiment. So we recruited 20 participants and we conducted an experiment, and we found something interesting. That for arousal, that the patterns worked really well. For valence, not as well, particularly for negative valence. And probably when speaking to many of these participants, everybody kind of described vibrotactile stimulation motion as a pleasant experience. So it was really difficult to simulate negative emotions. Then we decided to explore this further and see what are other applications for effective haptics, and one was pain distraction. We wanted to study whether tactile stimulation can influence pain distraction, and we did this experiment where the user experiences a VR game where a small ball lands onto their palm, and then we give this a random buzz of energy, jumps off their palm, and then they have to keep it in. So this is the kind of exercise that they have to do. At the same time, they would receive tactile stimulation feeling the ball or not. And we wanted to see if there is any effect of tactile stimulation, and we used the cold pressor test to simulate pain, and we found also very interesting results. Those are that even though there was differences between VR and no distraction groups, but we found statistically significant differences between the group using VR plus tactile compared to the no distraction group. And then we noticed that there are kind of two different distributions. So when we plot the histogram of the data, we found bipolar distribution. So we decided to break this down into further two different groups: low pain tolerance, high pain tolerance. And we found also that there was statistically significant difference between the VR plus tactile and VR only groups. Next, we try to investigate and see whether there are other applications for effective haptics, and in particular, we wanted to use vibrotactile stimulation for alerting a sleeping person. And for that, we had to look for two things. One, trying to create an arousing signal, at the same time a pleasant one, so that they have minimum inertia as they wake up. But before doing this, trying this out with sleeping people, we decided to look in particular into exogenous attention during a wake. So we did an experiment where participants look for a visual cue, and they get vibrotactile stimulation, and we wanted to see how effective this vibrotactile stimulation for activating or influencing exogenous attention. So in terms of the vibrotactile stimulations, we looked into three different patterns. One was continuous tactile stimulation, where you feel apparent tactile motion; discrete, where you feel vibration discretely at individual points; or simultaneous, where all the vibration motors are activated at the same time. And then we found, again, some interesting results. Just to summarize this, we found that continuous tactile stimulation was the most pleasant, the most positive, highest valence, and yet the most arousal. So we decided that this is promising, this is interesting, let's try this out with sleeping people, and that took us a bit of effort to get an RB application for that, but ended up well. So we recruited 10 participants, we asked everyone to use this armband and use it for waking up as an alarm. For 6 days, trying the 3 different patterns over 6 days in total. And we also found very interesting results. We found that continuous tactile stimulation was rated highest, statistically significant results. That they were rated the highest, they were rated the most pleasant, which means probably continuous tactile stimulation could be a good way to wake people up in a very pleasant yet arousing way. We also found that there are also individual differences. We talked about this yesterday. In conclusion, we believe that mediated touch can influence human emotions. We need to be careful about how we design these. And in particular, it seems like tactile stimulation serves really good attention. Next, I want to take you very quickly over haptic guidance, what we did. We developed a system that can provide haptic guidance. We developed different haptic guidance methods. We developed full haptic guidance, partial guidance, and disturbance guidance. In disturbance guidance, the way we develop this is trying to look for interesting attention points on the handwriting task, and then provide some buzz vibrotactile stimulation just to keep people's attention to the task. We developed quantitative evaluation method that can take into consideration all the different aspects of handwriting, including stroke sequence, speed, accuracy of handwriting, etc. Then we conducted an experiment with adults at the beginning, trying to investigate whether full guidance, partial guidance would do better. We found that both improved the quality of learning, except the results were not really statistically significant for this group. Then we decided to combine and see whether a combination of partial full guidance could even improve any better, and we found some good results. So we found that the combination of starting with partial and then use full guidance actually has worked even better than using merely full or partial guidance, and we found this even better than starting with full guidance then followed by partial guidance. One possible explanation is, as you're learning the gross aspects of a handwriting skill, partial guidance is better because it's more interactive, but as you're after a very specific, very fine details of the motor skill, probably full guidance would do better. Then we tried to, and then we found those results, as you see here, that there are statistically significant results for combining partial and full guidance methods than using merely full or partial guidance. Next is to try this with children. So we recruited 40 different children from Cranley School in Abu Dhabi, and then we conducted this over a semester-long 11 weeks experiment. And this is the task, so the children would exercise with this system for 3 days. At the end of the week, they do a test, which is paper-based and computer-based, and we try to evaluate their improvement and their progress. So we found some interesting results. We tried with 10 different characters. These are English characters. And we found that for low complexity characters, such as I, for example, full guidance has worked probably the best. But then for kind of medium complexity letters, and this is the classification that the teachers actually provided, it seems like full and partial guidance work better. But for high complexity shapes, it seems like disturbance mode has worked best, and that was a little bit of surprise, but later on it makes sense because this keeps people attentive to the task. Then we also found a couple of other observations. Age group has an impact on the learning. For example, year 2 children develop better confidence because they could do the handwriting much faster, statistically significant results. We also found something that we're still exploring. We found that female participants like much better partial guidance. Now we're conducting an experiment with children with learning difficulties. In summary, haptic guidance needs to be adaptive. And of course, many factors influence it: the task, the age group, the gender potentially, and the learning method. Finally, I want to take you to a few slides talking about neural haptics, and the background of this is that we're using self-reporting, which is not really reliable, and we decided to look into other media, in particular trying to provide quantitative and objective data about the neural activation associated with tactile stimulation. We built this pilot study where we used a canvas display to provide tactile feedback on a screen where the user would just need to stroke the strings of a guitar in a very simple task. This is the task, and we found also very promising results. We found, for example, that on the middle frontal cortex, we found high activation of beta and gamma oscillations, and these oscillations, when we looked into cognitive processes, we found that this is highly correlated with attention. It also correlates with emotion. Of course, these are very preliminary results. We need to investigate this further. Then we also found there are also functional connectivity activities that are either enhanced or decreased due to the lack or to the presence of haptic feedback. In particular, on the frontal cortex, we found there are more interconnectivities when tactile feedback is provided. If you see on the lower side of the diagram, these areas are for somatosensory and motor areas, and this is where the activations, basically what the brain is trying to get to elicit more information because of the lack of the haptic data. We also found an interesting result that even though the application has nothing to do with emotion communication, there were implicit emotional communication, and people rated tactile feedback much higher in terms of emotions. So in conclusion, I want to say this is a very promising field. It's interesting. It gives us quantitative, reliable ways of measuring the brain activations associated with vibrotactile stimulation. Finally, I'd like to acknowledge my team. All this work is done by this group of young, talented people and my collaborators. And I'd like to thank you very much for your attention. I'm happy to discuss this now, or any of these projects now, or even later offline. Thank you.
How do you map the motion? How do you map the motion and contact?
Right. So the way we map this is we created a simple authoring tool. So we used lead motion to capture the position of your finger, and then we use two things. We use the speed to control the speed of the tactile stimulation, and then how far you go into the screen. That defines the intensity. So if you drag your finger further, it means you want to provide further intensity. And the way we thought about this kind of made sense, intuitive, is as you're reaching out to touch a person, if you push further, then probably you want more intensity, more pressure. And as you're stroking your finger across, that kind of defines the tactile stimulation.
But that is varied among subjects, right?
Of course, this is why we hired this focus group of 3 people, that they spent a lot of iterations trying to figure out what would work well for everybody. And then we get like a set of candidate patterns. One pattern could stimulate, let's say, low valence, low arousal, low valence, high arousal, and all these combinations. And now we moved on to hiring a larger group, and we confirm these.